August 1, 1943, Boeing Field, Seattle, Washington. Test pilot Edmund T. Allen settled into the left seat of the XB-29 prototype, running through his pre-flight checks with methodical precision. The aircraft around him represented 4 years of intensive development and over $3 billion in government investment. It was the most technologically advanced bomber ever built, incorporating innovations that pushed the boundaries of what was possible with 1940s engineering. The engines roared to life, 4 massive Wright R3350 duplex cyclone radials, each producing 2,200 horsepower. Allen advanced the throttles, and the massive aircraft began rolling down the runway. The takeoff was smooth, the climb impressive. For 15 minutes, the test flight proceeded normally as Allen put the prototype through basic handling tests. Then fire broke out in the number 1 engine. Allen attempted to shut down the engine and extinguish the fire, but the flames spread. Within minutes, the wing structure was burning. Allen turned back toward the field, but the fire had already compromised the aircraft's structural integrity. The XB-29 crashed into a meatpacking plant near the field, killing Allen and his entire crew, plus 19 workers in the building. The disaster could have ended the B-29 program. The Army Air Forces could have concluded that the technology was too ambitious, the risks too great. Instead, they doubled down on development, pouring resources into solving the problems that had killed Allen and his crew. Because the strategic situation in the Pacific demanded a bomber that could fly higher and farther than anything else in existence. The story of the B-29 Superfortress is a story of engineering ambition meeting strategic necessity, of how America's industrial capacity and technical expertise created a weapon system that fundamentally changed the nature of strategic bombing. It's the story of a bomber designed to fly so high that enemy defenses couldn't reach it, and how that design requirement drove innovations that transformed aviation. By late 1939, American military planners recognized that any war with Japan would require strategic bombing of the Japanese home islands. Japan's industrial capacity was concentrated on the home islands, particularly around Tokyo, Osaka, and Nagoya. Destroying that industrial capacity would cripple Japan's ability to wage war. The problem was range. Japan was thousands of miles from any base that American forces could reasonably expect to control. The B-17 Flying Fortress, America's most capable heavy bomber in 1939, had a maximum range of about 2,000 miles with a modest bomb load. To reach Japan and return, a bomber would need to fly at least 3,000 miles, preferably more to allow for operational flexibility. The Army Air Corps issued a specification in January 1940 for a hemispheric defense weapon, capable of striking targets at intercontinental ranges. The official requirement called for a bomber that could carry a 2,000-pound bomb load for 5,333 miles at speeds over 400 miles per hour. The altitude requirement was equally demanding. The bomber had to be capable of operating at 35,000 feet, well above the effective ceiling of contemporary anti-aircraft defenses. These requirements were extraordinary by 1940 standards. No bomber in existence came close to meeting them. The engineering challenges were daunting. To achieve the required range, the aircraft would need enormous fuel capacity. To carry useful bomb loads at that range, it would need powerful engines. To operate at 35,000 feet, it would need pressurized crew compartments. To defend itself during long missions, it would need remote-controlled gun turrets. Boeing's design team, led by Chief Engineer Wellwood Beale, approached the problem systematically. They started with the most fundamental requirement, range. The aircraft would need a very high lift-to-drag ratio to achieve fuel efficiency. This drove them toward a clean aerodynamic design with a high aspect ratio wing, minimal drag from protrusions, and careful attention to every detail that might increase drag. The wing design was critical. Boeing engineers developed a very high aspect ratio wing with advanced laminar flow airfoil sections. The wing was extraordinarily long and thin compared to contemporary designs, providing excellent lift-to-drag characteristics but requiring complex structural engineering to handle the loads. The wing area was 1,736 square feet, enormous by the standards of the day. The engines were perhaps the biggest challenge. The Wright R3350 duplex Cyclone was selected as the power plant. It was a massive 18-cylinder radial engine designed to produce 2,200 horsepower, but in 1940, the engine existed only on paper. Wright Aeronautical would have to develop it from scratch while Boeing was designing the aircraft around it. The pressurization requirement added complexity. At 35,000 feet, the outside air pressure is about 1/4 of sea level pressure, and the temperature is typically 40 degrees below 0 Fahrenheit. Humans can't survive in those conditions without pressure suits or pressurized compartments. The B-29 would need to maintain sea level pressure inside the crew compartments while operating at extreme altitude. No existing bomber was fully pressurized. Some aircraft had pressurized cockpits, but the B-29 would need multiple pressurized compartments connected by a pressurized tunnel. The engineering challenges included designing pressure-tight structures, creating airlocks for entry and exit, and developing systems to maintain pressure, even if the aircraft suffered battle damage that punctured the pressure hull. The defensive armament requirement led to remote-controlled gun turrets. Conventional gun turrets required gunners to sit in exposed positions, enduring extreme cold and wind. Remote control would allow gunners to sit in pressurized compartments while aiming and firing guns in external turrets, through periscopic sights. The concept was innovative but unproven. Boeing's design incorporated 4 remote-control turrets, 2 on top of the fuselage, 1 on the bottom, and 1 in the tail. A sophisticated fire control system allowed any gunner to control multiple turrets, concentrating fire against attacking fighters. The system included analog computers that calculated lead angles in ballistics, revolutionary technology for 1940. The final design that emerged was unlike anything that had flown before. The B-29 would be 99 feet long with a 141-foot wingspan. It would weigh over 135,000 pounds fully loaded, more than twice the weight of a B-17. The 4 R3350 engines would provide 8,800 total horsepower. The theoretical performance included a cruising speed of 290 miles per hour, a service ceiling of 36,000 feet, and a maximum range exceeding 5,000 miles. Boeing received a contract for 3 XB-29 prototypes in September 1940, an extraordinarily early commitment given that the design was still preliminary. The Army Air Forces were gambling that Boeing could solve the technical problems, because the strategic situation allowed no time for conventional development timelines. The engine development proved even more challenging than anticipated. The R3350 was an enormously complex engine, pushing the boundaries of what was possible with 1940s metallurgy and manufacturing. It ran extremely hot, creating reliability problems that plagued the program throughout development. Cylinders cracked, valves failed, cooling systems were inadequate. Each problem required months to diagnose and fix. The airframe development proceeded in parallel with engine development, adding risk. Boeing was designing an aircraft around an engine that didn't yet work reliably. If the R3350 couldn't be made reliable, the entire program would fail. Yet there was no time to wait for the engine to be perfected before proceeding with airframe design. The pressurization system required solving problems that no one had faced before. How do you create airlocks that crews can use while wearing bulky flight gear? How do you route control cables and wiring through pressure bulkheads without creating leak paths? How do you ensure that the pressure hull remains intact when the aircraft suffers battle damage? Each question required innovative engineering solutions. The remote-controlled gun turret system was extraordinarily complex. The fire control computers had to calculate ballistics in 3 dimensions while accounting for the aircraft's speed and attitude. The gun turrets had to track fast-moving fighters with enough accuracy that gunners could achieve hits at ranges of several hundred yards. The control systems had to be reliable enough to function throughout missions lasting 10 or more hours. The first XB-29 flew in September 1942, more than a year behind the original schedule. The test flight revealed numerous problems. The engines overheated. The pressurization system leaked. The remote gun turrets malfunctioned. The flight controls were heavier than expected. Each problem required engineering investigation and design modifications. Then came the August 1943 crash that killed Edmund Allen. Investigation revealed that the engine fire had started due to inadequate cooling combined with a magnesium crankcase that burned once exposed to flame. The loss of the prototype and test crew was devastating, but the program continued. Too much was invested and the strategic need was too great to turn back. Boeing and Wright Aeronautical threw resources at solving the engine problems. Improved cooling systems were designed. Magnesium components were replaced with steel. Cylinder head designs were modified. Fuel injection systems were refined. Each modification required testing and validation, but the problems were gradually overcome. The production decision had already been made before the prototype crashed. The Army Air Forces, desperate for B-29s to execute the strategic bombing campaign against Japan, ordered production to begin even though development wasn't complete. This decision, known as concurrency, was extraordinarily risky. If the design problems couldn't be solved, thousands of unusable aircraft might be produced. Production began at 4 massive facilities: Boeing's plants in Wichita, Kansas and Renton, Washington, Bell Aircraft in Georgia, and Martin in Nebraska. At peak production in 1944, these factories would produce over 350 B-29s per month. But in late 1943 and early 1944, they were producing aircraft with known deficiencies that would require modification before they could be used in combat. The costs were staggering. The B-29 program consumed over $3 billion, more than the Manhattan Project that developed the atomic bomb. The program represented one of the largest investments in any single weapon system during the war. The gamble was that the B-29's capabilities would justify this enormous expenditure. The B-29 that emerged from this troubled development was an engineering marvel. Many of its features were revolutionary for the time and influenced aircraft design for decades afterward. The pressurization system maintained cabin pressure equivalent to 8,000 feet altitude while the aircraft flew at 30,000 feet or higher. This allowed crews to work in relative comfort without oxygen masks in the forward and aft crew compartments. The bomb bay remained unpressurized, but a pressurized tunnel allowed crew members to move between the forward and aft compartments during flight. The environmental control system that maintained pressurization also provided heating and ventilation. At 30,000 feet, outside temperatures could be minus 50 degrees Fahrenheit. The environmental system kept crew compartments at comfortable temperatures, allowing crews to maintain performance during missions lasting 12 hours or more. This was revolutionary compared to earlier bombers, where crews endured extreme cold that caused frostbite and degraded performance. The wing design achieved unprecedented efficiency. The high aspect ratio wing with its advanced airfoil sections provided excellent lift-to-drag ratios. The wing incorporated large Fowler flaps that extended rearward and downward for takeoff and landing, increasing wing area and lift coefficient. These flaps allowed the heavily loaded B-29 to operate from runways that would have been inadequate for an aircraft of its size with conventional flaps. The engines, despite their development troubles, were the most powerful radial engines then in production. Each R3350 displaced 3,347 cubic inches and employed 2 stages of supercharging to maintain power output at high altitude. The engines incorporated fuel injection, sophisticated ignition systems, and cowling designs that maximize cooling airflow. When properly maintained, they were capable of sustained operation at outputs that would have destroyed earlier engines. The propellers were equally advanced. Hamilton Standard developed 16.5-foot diameter 4-blade constant-speed propellers. Specifically for the B-29, the propellers incorporated reversible pitch for braking after landing, a feature that improved safety when operating from the sometimes short runways in the Pacific Theater. The remote-controlled defensive armament system was unlike anything previously deployed. The gunners sat at sighting stations with periscopic sights connected to analog computers. When a gunner tracked a target, the computer calculated the correct lead angle, accounting for the target's speed, the aircraft's speed, and ballistic drop. The computer then directed the turrets to fire at the calculated lead angle. The system allowed concentration of fire. Multiple turrets could be directed against a single attacker, creating a density of fire that few fighters could survive. The central fire control system coordinated the turrets to avoid conflicts when multiple gunners tracked different targets. The sophistication of this system anticipated by decades the computer-controlled weapon systems of modern combat aircraft. The bomb bay was enormous, capable of carrying 20,000 pounds of bombs over short ranges or 12,000 pounds on long-range missions. The bombs were carried vertically in tandem bays, allowing efficient packing of ordnance. The bay doors were designed to open rapidly and close quickly, minimizing the time the bay was exposed to outside air at high altitude. The navigation and bombing systems incorporated the latest technology. The B-29 carried radar systems that allowed navigation and target identification through clouds and darkness. The NAPQ-13 radar provided ground mapping capability, while the NAPQ-7 Eagle radar system, introduced later, could identify specific targets from high altitude. These radar systems made the B-29 capable of operating effectively in conditions that would have grounded earlier bombers. The flight deck featured innovations that improved crew efficiency. The pilot and co-pilot sat side by side with excellent visibility through large windows. The instrument panel was organized logically with engine instruments grouped together and flight instruments positioned for easy scanning. The autopilot system could maintain heading, altitude, and airspeed for extended periods, reducing crew workload during long overwater flights. The first B-29s arrived in India in spring 1944 for Operation Matterhorn, the campaign to bomb Japan from bases in China. The operation highlighted both the B-29's capabilities and the logistical challenges of operating such a sophisticated aircraft far from support infrastructure. The concept was to base B-29s in India, fly them over the Himalayas to forward bases in China, refuel and load bombs in China, and then attack targets in Japan, Manchuria, and Southeast Asia. The reality was that each bombing mission required multiple transport flights over the Himalayas to deliver the fuel and bombs that one B-29 would carry to target. The logistics were absurd. It took 7 B-29 transport flights over the hump to deliver enough fuel and ordnance for one B-29 combat mission. The operational efficiency was terrible, but it was the only way to reach Japanese targets from land bases until American forces captured islands closer to Japan. The missions demonstrated the B-29's capabilities despite the logistical constraints. The bombers could operate at altitudes where Japanese fighters struggled to intercept them. When fighters did reach the B-29's altitude, they found the bombers heavily defended by the remote-controlled gun turrets. Japanese anti-aircraft fire was largely ineffective against targets at 30,000 feet, exactly as the B-29's designers had intended. But the operational tempo from China bases was unsustainable. The logistical demands consumed too many aircraft and too much fuel to deliver meaningful bomb tonnages against Japanese targets. Strategic planners understood that the B-29 offensive would only become truly effective when bases closer to Japan could be secured. The capture of the Mariana Islands in summer 1944 provided the solution. Saipan, Tinian, and Guam were within 1,500 miles of Tokyo, well within the B-29's range. American engineers constructed massive airfields capable of supporting B-29 operations, including runways over 8,000 feet long and extensive maintenance and supply facilities. The first B-29 raid from the Marianas struck Tokyo on November 24, 1944. Raid involved 111 B-29s flying from Saipan, a 3,000-mile round trip that took over 13 hours. The altitude was approximately 30,000 feet, above the effective ceiling of most Japanese anti-aircraft guns. Damage to the target was modest, but the raid demonstrated that Japan's home islands were now within reach of sustained strategic bombing. The high-altitude precision bombing doctrine that guided early missions proved disappointing. At 30,000 feet, even with sophisticated bomb sights, accuracy was poor. The jet stream winds over Japan, often exceeding 200 miles per hour, made bombing even more difficult. Bombs released at high altitude were blown hundreds or thousands of yards off target by winds. The precision bombing that had been central to American strategic bombing doctrine wasn't working. Major General Curtis LeMay, who took command of the 21st Bomber Command in January 1945, made the controversial decision to switch to low-altitude night incendiary attacks. The new tactics sacrificed the altitude advantage that the B-29 was designed around, but dramatically improved bombing accuracy and effectiveness. Bombers would attack at 5,000 to 8,000 feet below the altitude where jet stream winds were strongest and where bomb sights were more accurate. The first low-altitude incendiary raid against Tokyo on March 9 to 10, 1945 was devastatingly effective. Over 300 B-29s attacked from altitudes around 7,000 feet, dropping incendiary bombs that created firestorms across Tokyo's densely built districts. The raid killed an estimated 100,000 people and destroyed 16 square miles of the city. It was one of the most destructive single bombing missions in history. The shift to low-altitude tactics made B-29s more vulnerable to anti-aircraft fire and fighter interception. Losses increased compared to high-altitude missions. but the bombing effectiveness improved so dramatically that LeMay judged the trade-off acceptable. The B-29's defensive armament, designed for high-altitude bomber defense, proved effective at lower altitudes as well. Japanese fighters attempting to intercept the bomber streams suffered heavy losses to the concentrated defensive fire. Through spring and summer 1945, the B-29 offensive intensified. Raids involving 500 or more bombers became routine. Japanese cities were systematically destroyed, not just the industrial areas but entire urban districts. The combination of high explosive and incendiary bombs created firestorms that firefighters couldn't control. By July 1945, most major Japanese cities had been largely destroyed. Despite the shift to low-altitude tactics, the B-29's ability to operate at extreme altitude remained strategically important. The knowledge that B-29s could bomb from 30,000 feet or higher influenced Japanese defensive planning and forced Japan to maintain air defenses that might otherwise have been deployed elsewhere. Japanese interceptor aircraft struggled to reach 30,000 feet with useful performance. The Ki-44 Tojo and Ki-84 Frank fighters could barely reach that altitude and had little maneuverability once they got there. The Ki-100, perhaps Japan's best late-war fighter, was more effective at high altitude, but was produced in limited numbers. Japanese pilots attempting high-altitude interceptions faced oxygen starvation, extreme cold, and fighters that responded sluggishly to controls. The Japanese Army developed specialized high-altitude interceptors specifically to combat B-29s. Ki-108 was a pressurized version of the Ki-102 twin-engine fighter designed to operate effectively at 40,000 feet. Only a handful were built before the war ended. The projects demonstrated how much the B-29's altitude capability concerned Japanese defense planners, forcing them to invest resources in countermeasures. Japanese anti-aircraft artillery was similarly challenged. Heavy anti-aircraft guns of 75mm to 120mm caliber had maximum effective ceilings around 25,000 to 30,000 feet. Against B-29s at 30,000 feet or higher, the guns were operating at the limits of their capability. Shell trajectories were affected by high-altitude winds. Fuse settings became less reliable at extreme ranges. Hit probabilities dropped dramatically compared to lower-altitude targets. The altitude advantage meant that even when B-29s conducted high-altitude missions, losses to enemy action were relatively low. During 1945, the loss rate was approximately 1.4% per mission, low compared to the 5% to 7% loss rates that B-17s and B-24s had suffered over Germany before achieving air superiority. The B-29's altitude capability and heavy defensive armament made it extraordinarily difficult to shoot down. The psychological impact of bombing from unreachable altitudes affected Japanese morale. When air raid sirens sounded and civilians took shelter, they knew that bombers were approaching that their defenses couldn't effectively stop. The contrails of B-29s at high altitude became visible symbols of American air superiority and Japanese vulnerability. Propaganda that claimed Japanese defenses were effective became obviously false when bombers operated with impunity over Japanese cities. The B-29 underwent continuous modification throughout its operational life as lessons from combat operations were incorporated into the design. These modifications improved performance, reliability, and combat effectiveness. Engine reliability remained a persistent concern. The R3350 was pushed hard in service, often operated at power settings and temperatures that stressed components. Engine failures remained more common than desired, though intensive maintenance programs reduced failure rates substantially compared to early operations. Improved cylinder head designs, better cooling baffles, and refined operating procedures gradually made the engine more reliable. The gun turret systems were modified based on combat experience. Early turrets had reliability problems, with guns jamming and turret drives failing. Improved ammunition feed systems reduced jamming. More robust turret drives better withstood the sustained firing that combat demanded. Software updates to the fire control computers improved accuracy and made the system more intuitive for gunners. The tail gunner position received special attention. The tail was the most common direction from which Japanese fighters attacked, making the tail gunner position critical. The tail turret was improved to provide better fields of fire and faster tracking rates. Some B-29s had their tail turrets upgraded to 4-gun installations rather than the standard 2 guns. doubling the defensive firepower in the most vulnerable sector. Radar systems were progressively upgraded. The NAPQ-7 Eagle radar, introduced in early 1945, provided dramatically better resolution than earlier systems. The Eagle radar could identify specific buildings from 30,000 feet, allowing precision targeting even through clouds. This capability made the B-29 effective in all weather conditions, unlike earlier bombers that required visual conditions for accurate bombing. The defensive armament was sometimes reduced to increase performance. Some B-29s operating over Japan in the war's final months had turrets removed to save weight. The reduced weight allowed higher bomb loads or better performance. Japanese fighter resistance had declined to the point where the risk of removing defensive guns was acceptable to gain the performance advantages. Special mission variants were developed for specific roles. The F-13 reconnaissance variant had cameras installed in the bomb bay and additional fuel tanks for extended range. The B-29B was a stripped-down version with reduced defensive armament, used for low-altitude night attacks where heavy defensive guns were less necessary. The modifications demonstrated the basic design's flexibility and adaptability. The most historically significant B-29 missions were the atomic bomb attacks on Hiroshima and Nagasaki in August 1945. These missions required special modifications and intensive training, leveraging the B-29's capabilities while adapting the aircraft for a completely unprecedented mission. The atomic bomb was extraordinarily heavy. Little Boy, the uranium bomb dropped on Hiroshima, weighed 9,700 pounds. Fat Man, the plutonium bomb used against Nagasaki, weighed 10,800 pounds. Both bombs were also physically large, requiring modifications to the B-29's bomb bay to accommodate them. The 509th Composite Group, formed specifically for the atomic bomb missions, received specially modified B-29s designated Silver Plate. These aircraft had their gun turrets removed except for the tail position, reducing weight. The bomb bay was extensively modified with special release mechanisms. Additional fuel tanks provided extended range. The modifications made the Silver Plate B-29s among the fastest and longest-ranged variants. The Enola Gay, the B-29 that dropped Little Boy on Hiroshima on August 6, 1945, flew the mission at moderate altitude, releasing the bomb from approximately 31,000 feet. The altitude was necessary to allow the aircraft to escape the blast effects. After bomb release, pilot Paul Tibbets immediately put the aircraft into a diving turn away from the target, accelerating to maximum speed to increase the distance before detonation. The bomb detonated at approximately 1,900 feet above Hiroshima with a yield equivalent to about 15 kilotons of TNT. The Enola Gay was about 11 miles away when the bomb detonated. Even at that distance, the crew felt the shock wave as the aircraft was buffeted by the blast. The mushroom cloud rose to over 50,000 feet, higher than any B-29 could fly. The Nagasaki mission 3 days later encountered more difficulties. Cloud cover obscured the primary target, forcing the crew to divert to Nagasaki, a secondary target. Fuel consumption was higher than planned due to the extended flight time. The bomb was released from about 29,000 feet, with Fat Man detonating at approximately 1,650 feet altitude with a yield around 21 kilotons. Both missions demonstrated the B-29's capabilities: range to reach targets deep in Japan, altitude to escape blast effects, precision navigation and bombing to hit specific aim points, and reliability to complete extraordinarily critical missions without mechanical failure. The atomic missions weren't typical B-29 operations, but they showcased what the aircraft could do when everything worked perfectly. The B-29 offensive against Japan achieved strategic effects that went beyond the physical destruction of cities and industries. The campaign demonstrated America's capability to project power across thousands of miles of ocean and destroy targets that Japanese forces couldn't effectively defend. The destruction of Japanese industrial capacity was substantial. By mid-1945, aircraft production had fallen to a fraction of earlier levels due to bombing damage to factories and disruption of component suppliers. Oil refineries were destroyed, crippling Japan's ability to produce fuel. Transportation networks were severed, preventing movement of materials and finished goods. The cumulative effect was economic collapse. The civilian toll was enormous. Estimates suggest that strategic bombing killed between 300,000 and 900,000, Japanese civilians with millions more rendered homeless. The ethical questions raised by this civilian targeting remain contentious. The bombing campaign represented total war carried to its logical extreme, where civilian populations became targets to break enemy morale and productive capacity. Japanese military forces were affected despite not being the primary targets. The destruction of transportation networks hindered movement of troops and supplies. The diversion of resources to air defense, including fighters, anti-aircraft guns, and radar systems, meant fewer resources for other military needs. The psychological impact on military personnel who saw their country being destroyed from the air affected morale and willingness to continue fighting. The B-29 offensive contributed to Japan's decision to surrender, though how much it contributed compared to other factors remains debated. The atomic bombings, carried out by B-29s, clearly influenced the surrender decision. The conventional firebombing campaign had already destroyed much of Japan's urban areas and industrial capacity, creating conditions where continued resistance seemed futile. The Soviet entry into the war and the destruction of Japan's Kwantung Army in Manchuria also influenced the decision. What's indisputable is that the B-29 enabled strategic bombing of Japan on a scale that would have been impossible with any other bomber. The B-17 and B-24 lacked the range to reach Japan from available bases. British heavy bombers similarly lacked the range and altitude performance. Only the B-29 could fly the distances required, operate at the altitudes needed, and deliver the bomb tonnages necessary for sustained strategic bombing. The B-29 remained in service long after World War II ended. During the Korean War from 1950 to 1953, B-29s flew bombing missions against North Korean and Chinese forces. The aircraft that had been designed to bomb Japan from high altitude was used for tactical bombing of bridges, supply depots, and troop concentrations at much lower altitudes. Korean War operations revealed how much aviation had advanced in just 5 years. Soviet-supplied MiG-15 jet fighters could easily intercept B-29s, forcing the bombers to operate at night or with heavy fighter escort. The altitude advantage that had made the B-29 relatively invulnerable against Japanese defenses was negated by jet fighters that could climb to 50,000 feet. The B-29's operational career was clearly ending as jet bombers began entering service. The B-29's technological legacy extended far beyond its operational service. Many of its innovations became standard features of subsequent aircraft designs. Pressurized cabins became standard on long-range aircraft. Remote-controlled defensive systems influenced bomber design through the 1950s. The high-aspect ratio wing designs, pioneered on the B-29, influenced jet airliner design. The Soviet Union's Tu-4 bomber was a reverse-engineered copy of the B-29, 3B-29S, made emergency landings in Soviet territory during World War II and were interned. Stalin ordered them copied exactly, resulting in the Tu-4 that entered Soviet service in 1949. The Tu-4 gave the Soviet Union a strategic bomber capability and demonstrated how significant the B-29's technology was. The production techniques developed for the B-29 program influenced post-war aerospace manufacturing. The massive factories, the production management systems, and the quality control procedures became models for manufacturing other complex aircraft. Boeing's experience with the B-29 positioned the company to become the dominant commercial airliner manufacturer in the post-war era. Behind the technical achievement and strategic success were the men who flew the B-29s into combat. These crews faced dangers that statistics only partially capture. Each mission was a test of endurance, skill, and luck that lasted 10 to 15 hours. The typical B-29 crew consisted of 11 men: aircraft commander, pilot, bombardier, navigator, flight engineer, radio operator, radar operator, and 4 gunners. These men trained together for months before deployment, developing the coordination and trust essential for survival in combat. They knew each other's strengths and weaknesses, could anticipate reactions, and functioned as an integrated team. Captain Robert Morgan, who had previously commanded the Memphis Belle B-17 in Europe, transferred to B-29s for the Pacific Campaign. He described the B-29 missions as more physically exhausting than his European missions despite the pressurized cabin and greater comfort. The sheer length of missions, often exceeding 12 hours, created fatigue that degraded performance and judgment as missions progressed. The flight from the Marianas to Japan and back covered over 3,000 miles, mostly over open ocean where an engine failure or navigation error could be fatal. Crews climbed to altitude over empty ocean, navigated by dead reckoning and celestial observations to reach Japan, conducted their bombing runs while being shot at, and then faced the long flight home. The return flight was particularly stressful because fuel was always marginal and battle damage might have created problems that wouldn't become apparent until systems were stressed. Ditching in the ocean was a constant fear. A B-29 that lost too many engines to make it back to base had to attempt a water landing, a maneuver that killed or injured crew members even when executed perfectly. The ocean swells in the Pacific could be 20 feet or higher. Landing a 135,000-pound aircraft on moving swells in darkness frequently resulted in the aircraft breaking apart on impact. Survival rates for ditching crews improved as the war progressed and submarine rescue capabilities were enhanced, but ditching remained extremely dangerous. Weather added to the dangers. The jet stream over Japan created wind conditions that made navigation difficult and bombing inaccurate. Typhoons forced cancellation of missions or, worse, caught formations in flight with violent turbulence that damaged aircraft and injured crews. Icing conditions at high altitude could accumulate on wings and control surfaces, degrading performance and creating control problems. Combat damage created life-threatening situations that required skill and composure to survive. Flak could damage engines, puncture fuel tanks, wound crew members, or damage flight controls. Fighter attacks could destroy critical systems in seconds. Crews had to assess damage, implement emergency procedures, and decide whether to continue to target, abort the mission, or attempt emergency landings at alternate fields. The physical environment inside a damaged B-29 could become nightmarish. If the pressurization was lost due to battle damage, crew members had to don oxygen masks while dealing with sudden decompression and temperatures that plummeted to 40 below zero. Wounded crew members needed immediate treatment, but the crew positions were separated and reaching an injured crewman might require depressurizing the aircraft or using the crawl tunnel between compartments. Fire was perhaps the most terrifying danger. Engine fires could spread to wing fuel tanks, creating situations where the aircraft had minutes before structural failure. Crew members fighting fires while wearing oxygen masks and dealing with battle damage required extraordinary courage and skill. Some crews successfully fought engine fires and completed missions on 3 or 2 engines. Others weren't so fortunate. The psychological toll accumulated over successive missions. Each crew was assigned to complete 35 combat missions, a tour of duty that could take 6 months or more depending on operational tempo. Early missions were terrifying as crews learned what combat was actually like. Middle missions became routine, a dangerous mindset that could lead to complacency. Late missions were nerve-wracking as crews counted down to completing their tours, knowing that many crews were shot down on their final missions. Some crew members broke under the stress. Combat fatigue, what would later be called PTSD, affected crews who survived sustained combat. Symptoms included nightmares, inability to sleep, hypervigilance, and emotional numbing. The Army Air Forces had medical officers who could ground crew members suffering combat fatigue, but many men struggled through their symptoms because they didn't want to let down their crew. The losses were substantial. 21 Bomber Command, operating from the Marianas, lost 414 B-29s to all causes during the campaign. Not all losses were due to enemy action. Mechanical failures, accidents, weather, and operational problems accounted for a significant percentage. But each loss represented 11 men killed, captured, or missing, plus the loss of an aircraft that cost $600,000 and required months to replace. Some crews were shot down and became prisoners of war. Japanese treatment of captured B-29 crews was often brutal. The crews had been bombing Japanese cities, killing civilians, and Japanese authorities and civilians viewed them as war criminals rather than legitimate combatants. Some captured airmen were executed, others were beaten, starved, or tortured. Survival as a POW in Japan required endurance that many didn't have. Yet the missions continued. New crews replaced those who completed tours or were shot down. The training pipeline in the United States produced a steady stream of replacement crews who underwent months of training on B-29s before deploying to the Pacific. By 1945, the training was sophisticated enough that new crews arrived in the theater with good proficiency on the aircraft and tactics, though nothing could fully prepare them for the reality of combat. The camaraderie among crews was intense. Men who shared the risks of combat missions formed bonds that lasted lifetimes. Reunions of B-29 crew associations continued for decades after the war, bringing together men who had faced death together over Japan. The shared experience of B-29 combat created connections that peacetime relationships rarely matched. Operating the B-29 required maintenance efforts that were unprecedented in their scale and complexity. Each aircraft required approximately 150 man-hours of maintenance for every hour of flight. With missions lasting 12 hours or more, this meant days of maintenance work to prepare an aircraft for its next mission. The ground crews who maintained the B-29s were unsung heroes of the campaign. These mechanics, many barely out of their teens, worked in difficult conditions to keep the aircraft flying. On Tinian, Saipan, and Guam, they worked outdoors in tropical heat and humidity, under sun that could cause heat stroke and rain that turned work areas into mud pits. The R3350 engines required constant attention. Cylinder head temperatures had to be monitored closely. Spark plugs fouled and needed replacement. Oil consumption was high and leaks were common. The engines accumulated carbon deposits that degraded performance and increased risk of detonation. Major engine changes, replacing an entire engine, were routine operations that maintenance crews could accomplish in a day when necessary. The complexity of the aircraft meant that maintenance required skilled specialists. Flight engineers understood the engines and fuel systems. Electrical specialists dealt with the sophisticated wiring and electrical systems. Hydraulics specialists maintained the systems that operated landing gear, flaps, and bomb bay doors. Radio and radar technicians kept the communication and navigation systems functional. Armament specialists maintained the remote gun turrets and fire control computers. The maintenance schedule was intensive. After each mission, crews debriefed with maintenance personnel about any problems encountered during flight. Maintenance crews conducted post-flight inspections, checking systems, looking for damage, and performing routine servicing. Between missions, more extensive inspections examined components that might be wearing or developing problems. After a certain number of flight hours, aircraft underwent major inspections that essentially disassembled and inspected every critical system. Battle damage repairs added to the workload. Aircraft returning from missions often had flak damage, holes in wings or fuselage, damaged control surfaces, or destroyed systems. Sheet metal specialists fabricated patches to cover holes. Structural specialists repaired damaged frames and stringers. Hydraulics specialists bypassed damaged lines and replaced destroyed components. The goal was to return damaged aircraft to service as quickly as possible. The supply system supporting maintenance was a logistics achievement comparable to the aircraft itself. Spare parts had to be shipped from the United States across thousands of miles of ocean. Engines, propellers, tires, instruments, radio equipment, and thousands of smaller components had to be stocked at Pacific bases in sufficient quantities to support hundreds of aircraft. The supply pipeline took months, meaning that parts ordered today wouldn't arrive for 3 or 4 months. Maintenance crews improvised when proper parts weren't available. They fabricated parts from raw materials. They cannibalized damaged aircraft for usable components. They modified components designed for other purposes to work in B-29 applications. This ingenuity kept aircraft flying when by-the-book maintenance would have grounded them for lack of proper parts. The maintenance officers who managed these operations faced constant pressure. Commanders wanted maximum numbers of aircraft available for missions. Maintenance officers had to balance this pressure against the need to properly maintain aircraft to prevent failures that could kill crews. The tension between operational demands and maintenance requirements was constant. Some maintenance practices would horrify modern safety officers. Mechanics worked on engines while they were running, making adjustments to carburetors or magnetos while standing next to spinning propellers. They worked at heights without safety harnesses, climbing on wings and fuselages to access components. They handled volatile fuels and explosive ordnance with minimal safety equipment. Accidents killed or injured maintenance personnel, though these casualties rarely appeared in the official records. The environmental conditions were brutal. Daytime temperatures on Tinian could exceed 100 degrees Fahrenheit with humidity that made the heat feel worse. Maintenance crews worked through this heat, often shirtless, risking sun exposure because the alternative was heat exhaustion. Nighttime brought mosquitoes and other insects. The coral dust that covered the island irritated skin and eyes and got into everything. Living conditions for maintenance personnel were Spartan. They lived in tents or crude huts constructed from salvaged materials. Meals were institutional and often monotonous. Recreation facilities were minimal. Mail from home took weeks to arrive. The isolation and boredom between periods of intensive work created morale problems that commanders struggled to address. Yet these maintenance crews kept the B-29s flying. The mission-capable rate for B-29s in the Marianas averaged around 70%. Remarkable for such complex aircraft operating in difficult conditions far from major support facilities. This achievement reflected the skill, dedication, and ingenuity of the ground crews who worked long hours in difficult conditions to keep the bombers operational. The bombing tactics employed by B-29 crews evolved dramatically over the course of the campaign as commanders learned what worked and what didn't. This evolution reflected both the aircraft's capabilities and the realities of combat over Japan. The initial high-altitude precision bombing doctrine emphasized attacking specific industrial targets from 30,000 feet. The theory was that the B-29's sophisticated bomb sights and radar systems would allow accurate bombing despite the altitude. Reality proved otherwise. The jet stream winds at high altitude over Japan were far stronger than anticipated, often exceeding 200 miles per hour. These winds made accurate bombing nearly impossible even with the best bomb sights. The bombing accuracy problem was quantified through strike photography and damage assessment. Raids that dropped hundreds of tons of bombs from high altitude often achieved less than 5% of bombs within 1,000 feet of the aim point. This level of accuracy was inadequate for destroying specific factories or facilities. The high-altitude precision doctrine was failing to achieve its objectives. Weather compounded the accuracy problems. Cloud cover over Japan was extensive, particularly during certain seasons. Visual bombing was impossible through clouds, and radar bombing was less accurate than visual bombing. Missions were sometimes scrubbed after flying most of the way to Japan because cloud cover prevented visual identification of targets. The operational inefficiency was frustrating to crews and commanders alike. Curtis LeMay's decision to switch to low-altitude night incendiary attacks represented a fundamental tactical shift. Instead of trying to destroy specific factories with precision bombing, the new approach aimed to destroy entire industrial areas with area incendiary attacks. Instead of attacking from 30,000 feet where winds made accuracy impossible, bombers would attack from 5,000 to 9,000 feet where winds were less problematic and bomb sights more accurate. The incendiary weapons were key to the new tactics. The M69 incendiary bomb was a 6-pound device filled with napalm that ignited on impact, spreading burning gel that adhered to whatever it touched. The bombs were packaged in clusters that broke apart after release, spreading individual bomblets across a wide area. A single B-29 could carry over 2,000 individual M69 bomblets. The low-altitude tactics required removing most defensive armament to save weight and increase bomb load. B-29s conducting low-altitude night attacks typically retained only the tail guns, removing the upper and lower turrets. This reduced weight by several thousand pounds, allowing increased bomb loads or fuel capacity. The tactic assumed that Japanese night fighter capabilities were limited enough that the reduced defensive armament was an acceptable risk. The first low-altitude incendiary raid against Tokyo on March 9 to 10, 1945 validated the new approach with horrifying effectiveness. The raid involved 334 B-29s attacking from altitudes between 4,900 and 9,200 feet. They dropped 1,665 tons of incendiaries across densely populated districts of Tokyo. The fires merged into a firestorm that created winds exceeding 100 miles per hour, pulling oxygen into the flames and creating temperatures that melted metal. The destruction was catastrophic. Approximately 16 square miles of Tokyo were burned out. Estimates of civilian deaths ranged from 80,000 to 100,000, making it one of the deadliest single bombing raids in history. Over 1 million people were rendered homeless. The industrial and economic damage was substantial, but the attack on civilian areas raised ethical questions that persist to this day. Japanese defenses struggled to cope with the low-altitude night attacks. Anti-aircraft guns had difficulty tracking targets in darkness. Night fighters existed, but in limited numbers and with inadequate radar or night vision equipment. The B-29's speed at low altitude gave defenders minimal time to react. By the time defenses recognized an attack was underway, the bombers had already dropped their loads and were departing. The success of the Tokyo raid led to similar attacks against other Japanese cities. Nagoya, Osaka, Kobe, and Yokohama were firebombed in March and April 1945. Each raid destroyed square miles of urban area and killed thousands of civilians. The pattern was consistent. Approach at low altitude at night, drop massive tonnages of incendiaries in concentrated patterns, create firestorms that overwhelmed firefighting capabilities. By June 1945, most major Japanese cities had been largely destroyed by incendiary attacks. Though the 21st Bomber Command began targeting smaller cities that previously would have been considered too minor to warrant strategic bombing attention. Cities with populations of 100,000 or less were systematically firebombed. The destruction of Japan's urban areas was reaching completion. The ethical questions raised by the incendiary campaign were recognized even at the time. Targeting civilian areas for destruction went beyond attacking industry or transportation. The firebombing created civilian casualties that far exceeded anything that precision attacks on military or industrial targets would have caused. Some officers expressed reservations about the tactics. But the prevailing view was that the attacks hastened Japan's defeat and therefore saved lives, overall by shortening the war. The daylight precision bombing missions continued alongside the night incendiary raids. Some targets required precision attack: oil refineries, aircraft plants, arsenals. These missions used the high-altitude tactics that the B-29 was originally designed for. The combination of night incendiary area attacks and day precision bombing created a round-the-clock offensive that gave Japanese forces no respite. Mining operations represented another tactical application of B-29 capabilities. Beginning in March 1945, B-29s conducted extensive mining of Japanese ports and waterways. The mines were sophisticated acoustic and magnetic types that could distinguish between warships and merchant vessels. The mining campaign, codenamed Operation Starvation, crippled Japanese shipping and contributed significantly to Japan's economic collapse. The mining missions required flying at low altitude over water at night to accurately place mines in designated channels and approaches. It was dangerous work that required precise navigation and timing, but the results justified the risks. Japanese shipping losses to mines eventually exceeded losses to submarines. The ports and waterways around Japan became so heavily mined that commerce virtually stopped. Supporting the B-29 offensive was an intelligence effort that gathered and analyzed information about Japan's industrial capacity, urban layout, defensive capabilities, and weather patterns. This intelligence determined targeting priorities, mission planning, and tactical approaches. Photo reconnaissance provided critical intelligence. Specially configured F-13 reconnaissance B-29s flew high-altitude photographic missions over Japan, bringing back detailed imagery of potential targets. The photographs were analyzed by specialists who identified industrial facilities, assessed bomb damage from previous raids, and provided detailed targeting information for upcoming missions. The reconnaissance missions were dangerous. Flying alone over Japan at high altitude, reconnaissance B-29s were vulnerable to interception by fighters that could concentrate against a single aircraft. The reconnaissance crews had no bombs to drop, just cameras. Their only defense was altitude, speed, and hope that Japanese fighters couldn't reach them, or that mechanical problems would force the fighters to break off attacks. Signal intelligence provided information about Japanese defensive capabilities and intentions. American code-breaking efforts gave insight into Japanese air defense deployments, fighter strength, and occasionally advance warning of tactical changes. Radio traffic analysis revealed patterns that indicated Japanese responses to American bombing tactics. This intelligence allowed American planners to avoid the strongest defenses or exploit weaknesses. Weather intelligence was crucial for mission planning. Long-range weather forecasting for the Pacific was primitive by modern standards, but meteorologists did their best to predict conditions over Japan days in advance. Forecasts determined whether missions would proceed, what altitudes would be used, and what tactics would be employed. Incorrect forecasts could result in missions encountering unexpected weather that prevented bombing or endangered aircraft. Human intelligence from Chinese resistance sources provided some information about conditions in Japanese-occupied areas, though the intelligence was of variable quality and often difficult to verify. After the war, intelligence from debriefing of Japanese prisoners and recovered documents filled gaps in understanding of Japanese defensive capabilities and decision-making. The target selection process combined intelligence with strategic planning. The Committee of Operations Analysts, based in Washington, analyzed which targets would most damage Japan's war-making capability. Industrial facilities, transportation networks, oil refineries, and urban areas were prioritized based on their contribution to Japanese military capacity. The targeting priorities evolved as intelligence revealed which sectors of Japanese industry were most critical and most vulnerable. Damage assessment after raids was challenging. Strike photography taken during missions showed immediate effects but couldn't reveal the full extent of damage. Follow-up reconnaissance missions days or weeks later showed recovery efforts and revealed which facilities had been successfully destroyed versus those that had been damaged but not disabled. The assessment informed future targeting decisions. By July 1945, Japan's situation was desperate. Most major cities had been largely destroyed. Transportation networks were crippled. Food distribution had broken down, creating shortages that approached famine conditions in some areas. Industrial production had collapsed. The nation was clearly defeated, yet the government showed no sign of surrendering. The B-29 offensive intensified during these final months. Missions involving 500 or more bombers became routine. The airfields in the Marianas operated at maximum tempo, launching and recovering aircraft around the clock. Crews flew missions every few days, with minimal rest between operations. The pace was unsustainable long-term but didn't need to be sustained long-term because everyone understood the war was approaching its end. The targeting shifted to whatever remained worth bombing. Medium and small cities that had escaped earlier attention were systematically destroyed. Rail yards and transportation nodes were attacked repeatedly. What remained of Japan's industrial capacity was targeted methodically. The objective was to make continuation of the war obviously futile by destroying everything that allowed Japan to function as an industrial nation. Leaflets were dropped warning civilians of upcoming attacks. The leaflets named cities that would be bombed and urged civilians to evacuate. The warnings were partly humanitarian, intended to reduce civilian casualties. They were also psychological warfare, demonstrating that American forces could bomb with such impunity that they could warn of attacks in advance and still carry them out successfully. The psychological impact on Japanese civilians was significant. Japanese defensive efforts were increasingly desperate. Kamikaze aircraft attempted to crash into B-29 formations. Fighters fitted with ramming weapons tried to physically collide with bombers, sacrificing themselves to bring down even one enemy aircraft. These desperate tactics reflected the hopelessness of Japan's strategic situation, but occasionally succeeded in destroying B-29s. The Soviet Union's entry into the war against Japan on August 8, 1945, 2 days after Hiroshima, added to Japan's catastrophic strategic position. The Kwantung Army in Manchuria, once Japan's premier military force, was crushed in days by the Soviet onslaught. Japan now faced enemies on all fronts with no remaining allies and no prospect of successful resistance. The atomic bomb attacks on Hiroshima and Nagasaki, delivered by B-29s, were the culmination of the strategic bombing campaign. These attacks demonstrated a new level of destructive capability that made continued resistance obviously suicidal. The psychological impact of atomic weapons went beyond their physical effects, creating an existential threat that conventional weapons, no matter how massive their cumulative destruction, didn't embody. Japan surrendered on August 15, 1945. The surrender was announced in Emperor Hirohito's radio address, the first time most Japanese civilians had heard their emperor's voice. The announcement ended the Pacific War and brought relief to American servicemen who had anticipated invading Japan's home islands in operations that would have cost hundreds of thousands of casualties. The B-29s that had spent months bombing, Japan flew one final mission, dropping supplies to Allied prisoners of war still held in Japanese camps. The supply drops delivered food, medicine, and clothing to prisoners who had endured years of brutal captivity. For many POs, the appearance of B-29s dropping supply containers rather than bombs was the first tangible evidence that the war had truly ended. The B-29 superfortress that flew higher than Flak could reach was more than just a technologically advanced bomber. It was a weapon system that embodied American industrial capacity, technological sophistication, and strategic reach. The $3 billion investment created an aircraft that could project power across the Pacific Ocean and attack targets that no other nation could reach. The aircraft wasn't perfect. The engine problems were never completely solved. The high-altitude precision bombing doctrine that drove the design proved less effective than anticipated. The operational costs were enormous, requiring massive support infrastructure and maintenance resources. The ethical questions raised by the strategic bombing campaign, particularly the firebombing of civilian areas, remain troubling decades later. But the B-29 accomplished what it was designed to accomplish. It flew missions that no other aircraft could fly. It delivered bomb tonnages that broke Japan's industrial capacity and will to resist. It provided the platform for the atomic bomb missions that helped end the war. The altitude capability that gave the aircraft its name proved less operationally important than anticipated. But the overall package of range, payload, and sophistication enabled strategic effects that justified the enormous investment. The story of the B-29's development from troubled prototype to war-winning weapon system demonstrates how technological innovation, industrial capacity, and strategic vision can combine to create capabilities that fundamentally change warfare. The aircraft that was too ambitious, too expensive, and too complex became the weapon that made victory in the Pacific possible on America's terms. For the crews who flew B-29s over Japan, the aircraft was simply their workplace, a complex machine that they maintained and operated despite its quirks and problems. They understood its limitations but also appreciated its capabilities. The pressurized cabin that let them fly in relative comfort. The altitude that usually kept them safe from fighters and flak. The range that brought them home after missions lasting most of a day. The reliability that, despite problems, got them to target and back more often than not. The B-29 that flew higher than flak could reach represents a moment when technology, strategy, and industrial capacity converged to create something unprecedented. It was the right aircraft for America's strategic situation in 1944-1945, enabling operations that would have been impossible with any other bomber. Its legacy lives on in every long-range bomber, every pressurized airliner, and every remotely controlled weapon system that traces its lineage back to the innovations pioneered by the engineers who created the superfortress.